Mice pie. Mice never tasted so delicious.
Well, today we are going to talk about a very famous paradox, the boy or girl paradox. Here is the problem. Now, family A has two children. Given that the older child is a girl, what is the probability that both children are girls? Family B also has two children. Given that at least one of them is a girl, what is the probability that both children are girls? Can you find out all these probabilities? Are these probabilities equal? The initial formulation of this question dates back to at least 1959, when Martin Gardner featured it in his October 1959 Mathematical Games column in Scientific American. Many thinks that these two probabilities are equal and they are 1/2. Well, is that right? How do you think? Pause this video if you want to give it a try. Please like this video and subscribe our channel to get more interesting math problems. This problem has the following underlying assumptions. 1. Each child is either male or female. 2. Each child has the same chance of being male as of being female. 3. The sex of each child is independent of the sex of the other. Under these three assumptions, we have the following four equally likely outcomes. 1. The older child is a girl. The younger child is also a girl. So we label this case as JGG. Second, the older child is a girl. The younger child is a boy. We label it as GB. 3. The older child is a boy. The younger child is a girl. And we label it as BG. And finally, the older child is a boy. And the younger child is also a boy. We label it as BB. Now let's consider problem 1. Family A has two children. Given that the older child is a girl, what is the probability that both children are girls? Now, here the condition is the older child is a girl, so we only have the following two situations. That is, the older child is a girl. Now, the 3 and 4, well, doesn't fit into this condition, so we do not consider them. We only consider outcome 1 and outcome 2. Now, based on these two outcomes, the possible outcomes here, what is the probability that both children are girls? As we can see, that's 1 out of 2. So the probability is 1 over 2. Now, let's consider the second problem. Now, family B has two children. Given that at least one of them is a girl, what is the probability that both children are girls? Now, in this case, because our condition is at least one of them is a girl, so the possible situation will be the following 3. 1, 2, 3. And in these 3 cases, at least one of them is a girl. Now, the fourth one does not satisfy this condition. So we do not consider it. We do not consider it. Now, among these three possible situations, now what is the probability that both children are girls? So that's what? 1 out of 3. So therefore, the probability for problem 2 is 1 over 3. Okay, so in summary, we have for the probability that both children are girls is 1/2 for the first problem, and the probability for that both children are girls is 1/3 for the second problem. Now, for those who have learned probability, we can also solve this question using conditional probability. Now, let's see how we can solve these problems using the formal definition of conditional probability. Now, following the classical probability arguments, we have the following. One, the sample space, which is the set S equals a set consisting of these 4 possible outcomes: GG, GB, BG, and BB. Let EA denote the event that the older child is a girl. Then this event EA is a set consisting of these 2 outcomes, GG and GB. Let EB denote the event that at least one of the 2 girls is one of the 2 children is a girl. Then EB is a set consisting of GG, GB, and BG. Now finally, let's consider let F be the event that both are girls. So in this case, F is the set consisting of only one outcome, that is GG, means they are both girls. So after defining all these events, we can use the formal definition of conditional probability to solve these problems. Let's consider problem 1. Family A has 2 children. Given that the older child is a girl, what is the probability that both children are girls? Now we can solve this one using the formal definition of conditional probability. So our event of interest is both children are girls. Now the event serves as the condition that the older child is a girl. So we can set up the equation here. Probability of F given that EA has already occurred. This equals, on the top, that's the probability of the intersection over the probability of the event, which serves as a condition. Now let's focus on the numerator. Since the event F is a subset of the event EA, so therefore the intersection of F and EA is simply F. So by substitution, we see this equals the probability of F over the probability of EA. Now again, on the top, that's the probability of the set consisting of only GG. On the bottom, that's the probability of the set consisting of GG and GB. And this equals, all right, on the top, that's a 1 out of 4. On the bottom, that's a 2 out of 4. So which equals 1 over 2. So that's the chance for problem 1. We found that the probability that both children are girls is 1/2, given that the older child is a girl. Now, let's consider problem 2. We're going to use conditional probability again. So family B has 2 children. Given that at least one of them is a girl, what is the probability that both children are girls? Here, the event of interest is, again, both children are girls. But the condition now is the event that serves as a condition became at least one of them is a girl. So we can set up this conditional probability as P of F given that EB has occurred. Now this equals, on the top, that's the probability of their intersection. On the bottom, that's the probability of the event which serves as a condition. Now again, since F is a subset of EB, now the intersection of F and EB is F. So this one equals probability of F over probability of EB. Now again equals probability of the event consisting of GG over the probability of the event consisting of 3 outcomes here, GG, GB, and BG. So it equals, on the top, that's 1 out of 4. On the bottom, that's 3 over 4. So which equals 1/3. That is to say, the probability that both children are girls is 1/3, given that at least one of them is a girl. So we use the definition of conditional probability to and find out that these probabilities, one is 1/2, the other is 1/3. I hope you enjoy this video, and thanks for watching. Have a good day.